we're going to start this new semester talking about solutions. This is also the first lecture in the quarter. It gives you an opportunity for a fresh start, part of your New Year's resolution maybe. So let's define solutions. A solution is a homogeneous mixture of two or more substances. Generally, the substance that's in the greatest availability or the greatest amount is called the solvent. And usually one of the components of a solution is identified as the solvent. And then everything else in the solution is called solute or solutes if there are more than one. And these are the other components of the solution, and they are generally present in a much lower concentration. So for example, here we have a little amount of powder on the left here that's potassium dichromate. It mixes with water, which is clear in the middle here, and forms an orange homogeneous liquid or solution. Now with potassium dichromate, this substance forms ions, and so when it reacts it looks like this. The potassium dissociates itself from the dichromate ion and independently flows through the solution independent of the dichromate ion. And we're going to look at how that occurs in just a little bit. Now, solutions have the following characteristics. First of all, they are homogeneous. Now, what that means is that after a solution is mixed and formed, if you take a sample, regardless of where you take the sample, the composition will be the same. So the composition is the same throughout, or is uniform. The physical state of the solution, whether it exists as a solid, a liquid, or a gas, is typically the same as the physical state of the solvent. And this, as you can see, if you look at table 11.1 in your book. So for example, if the solvent is a gas, then the solution will be a gas. If the solvent is a liquid, then the solution will be a liquid, etc. The components of the solution are dispersed in a molecular state. That means that they're broken apart to individual molecules, atoms, and or ions, depending on the type of solute that's involved. The dissolved solute in solution does not settle out or separate by physical means. In other words, if you leave a solution sitting on the counter, ultimately the solute will not settle to the bottom like a suspension will. And the composition of the solution, that is the concentrations of its components, can vary, but they vary within certain limits. There's a certain solubility, which we will talk about, that limits the composition that can be achieved. Now, an ideal solution is a solution that the intermolecular forces of attraction between solvent and solute species in a solution are no different than those that are present with the individual components. So if you look at the left and look at the intermolecular attractions occurring on the left, that they're the same as the intermolecular attractions on the right. Now, this is called ideal because this is not actually true. However, the change that occurs is so small that it allows us to disregard that in our calculations. Now, this is a representation of how dissolution occurs. And dissolution occurs, another word for solute going into solution, that occurs in 3 steps. The first 2 steps essentially represent the expansion of the solute and the solvent. Both of these have to expand molecularly to allow the intermingling of the components together. The third step called solvation. Now, breaking the bonds between solute molecules or between solvent molecules requires energy, and therefore that process is endothermic. However, when the molecules come together in the solvation process and the intermingling occurs, this generally releases energy because it's a lower energy state than the expanded solvent and solute molecules. Now, there are certain situations where this will not occur. Dissolution will not occur. And this is generally, for example, here you have oil and water, and the oil will not dissolute or separate to allow water in there, and water does not separate to allow the oil molecules in there. So a solution does not occur. And this leads to the rule of like dissolving like. Now, when it talks about like dissolving like, it's talking about the composition or properties of the solvent and the solute, and that they have to have similar properties for the separation and solvation to occur. And the most common of these properties is whether the solvent or solute is polar or nonpolar. So if you have two polar substances, a polar solvent and a polar solute, then they will dissolve. Or if you have two nonpolar substances, then they will dissolve. But if one is polar and the other is not polar, then they do not dissolve, and solvation does not occur. Now, as I said before, the separation part is an endothermic process, and initially when you dissolve a cold pack, that is, ammonium nitrate is dissolved in water, it absorbs heat, and in the process of absorbing heat, it causes the pack to become cold, and this is how a cold pack works. Now, in the process of solvation, sometimes the molecules remain intact. Sometimes they will totally dissolute into ions, and sometimes most of the molecules remain intact, but some will ionize. And so when the ionization occurs, it forms what's known as an ion or electrolyte. And this is a physical or chemical change that yields ions in solution. And we'll look at both the physical situation and the chemical situation in the upcoming slides. Now, as I said, some substances don't do that. If you dissolve alcohol in water, as on the left here, the alcohol molecules do not separate into ions, and no ions are yielded. Now, when that occurs, this solution does not conduct electricity. It's not a conductive. It has no conductivity. In the middle, you have a situation of strong electrolyte formation. And this is a situation where, with the physical chemical process, it generates ions, and in general, virtually 100% of the molecules, in this case potassium chloride, become potassium ions and chloride ions. And then on the right here you have the third situation, which is weak electrolyte formation. In that case, only a small fraction of the molecules become ions, and the rest remain intact molecules. And in that case, the conductivity occurs, but it is low. Now, here's a physical process that leads to the formation of ions. And this is the situation in this diagram. And what you have here is a ion-dipole interaction between the polar solvent, water, and the ionic components of potassium chloride. And you can see here that the potassium ions are sort of associated with the negative end, which is represented by the red of the water molecule, and that the positive end of the water molecule associates with the chloride ions. So in this case, it's a physical situation where ions are formed by this physical dispersal of the water, of the potassium ions and chloride ions in amongst the water molecules, and they totally surround each of the ions and solvate them and reduce the electrostatic interactions between the potassium chloride ions, so the solid potassium chloride crystals are broken apart in this process. So as this says, the potassium chloride dissolves in water and the ions are hydrated. The polar water molecules are then attracted to potassium ions and chloride ions, and the water molecules that are in front and behind are not shown in this diagram. Now here's the situation, I said physical or chemical. Now here's a chemical process that leads to the formation of ions. You have the combination of water with hydrochloric acid, and the hydrogen on the hydrochloric acid chemically reacts with the water molecule to form the hydronium ion and the chloride ion. So you have the ions forming in that way. So hydrochloric acid is an acid so that its molecule reacts with water and transfers this hydrogen ion to form the hydronium ion and the chloride ion. So the first process I showed you with potassium was a physical process that results in electrolytes. This one is a chemical process that similarly results in electrolytes. This reaction in this case is 100% complete. Therefore, hydrochloric acid is considered a strong acid, producing virtually 100% ions. Now, not all acids are strong acids, and in some cases, the vast majority of the molecules remain intact and do not form ions. Now here's the diagram to show the relationship between solubility, in this case on the y-axis measured in moles per liter, and temperature. And what you can see here is that as the temperature, in this case, we have all gases, and that as the temperature goes up, the solubility of a gas goes down. That's the solubility of a gas in water. So solubility is the maximum concentration that can be achieved under any particular conditions, and it is measured when the dissolution process is at an equilibrium. That is, it's not changing anymore. And a solution is called saturated when the solute's concentration is equal to its solubility. If it is not equal, if it is less than the solubility, then it's called unsaturated. And there are certain cases when it's more or greater than its solubility, and I'll show you how that can occur in a minute, and that's called supersaturated. So here you see that these gases are dissolved in water, and because they're gases, as the temperature increases, the solubilities all decrease. And in some cases less than others, but they all decrease as the temperature increases. And all of these solubilities have to be measured at the same pressure. Now you've all had the experience on the left here where you'll pour something into a glass, and if it's carbonated, it will produce bubbles. And what those bubbles are is the gas coming out of solution. And so these small bubbles of air in this gas of chilled water form when the water is warmed, because the solubility of the dissolved air is decreased, as we showed in the previous slide, and the bubbles will then form. So you take chilled water that has dissolved a certain amount of air, you warm it up, and because of that way that relationship is, you'll see these little bubbles of undissolved air form in the water. Now this problem of solubility can actually affect the fish in such a case that with increasing temperatures, the amount of dissolved oxygen in water can decrease, and it leads to fish dying for lack of oxygen. And this is the situation I mentioned before, where you open a carbonated beverage. When you open it, it reduces the pressure in the bottle, and the carbon dioxide comes out of solution and forms these bubbles. So the solubility of carbon dioxide is lowered and the dissolved carbon dioxide can be seen leaving the solution as small gas bubbles. This process of decreasing the solubility with a decrease in pressure is called Henry's law. Henry's law states that when you decrease the pressure of a solution, then the solubility of the gas decreases.